So first speaker is Simon Rudkin, who's in economics in Swansea and has joined us in social statistics. Is that right? Yes. And Simon's going to talk about inference on multidimensional data with topological data analysis ball mapper. So over to you, Simon.
Okay, so I'll close the chat. Right, so back to the, so the brief bio, as I was saying, I'm Dr. Simon Rudkin. I did my studies all in economics here in the University of Manchester, and have then worked variously around the world, and most recently in Swansea, before returning to Manchester as a senior lecturer in data science, but based in the social statistics department. Throughout my career, my research has really focused on the power of data and the stories that exist within data to help us understand sort of societal problems and then drive policy and things for benefits. So initially that would work within applied economics, but then, you know, has gone wider with various sort of policy applications. Okay, so basically what I'm going to argue today in this talk is that visualizing data is essential, and that when we start to see data, then we can start to see some of those stories that exist within the data. So the things that would drive my research. So inevitably as humans, we have a challenge. We can only see in 2 dimensions, maybe 3, but we struggle beyond that. Okay, and what we're going to argue is that if we can start to map and understand data in more dimensions, we can solve problems and understand better what's going on. Okay, so this talk is really using a strand of data science known as topological data analysis, and that's purely understanding the shape of data. So what we're going to do is we're going to put that within the context initially of this question. So how would we use constituency level data? So we're not talking big data sets here. Yeah, we're not going for many observations. What we're doing instead is taking a data that has a lot of variables, and how can we use that to understand the result of the 2016 EU referendum in the UK? Now, politically, of course, that has a huge amount of interest. It continues to have economic relevance, and therefore, if we can understand what happened, then we get some way to really working out going forward where we're going to be. So it's an ongoing debate, and we have a paper on this called An Economic Topology of Brexit. The working paper's online, and the journal version should be out quite soon. But in essence, we can think back to our research design, and we think about a research question, and then we start to think, well, what data, what information do we need to solve that? And of course, if we have more time, we could brainstorm, and these sorts of arguments come up. It was older people. It was perhaps lower income, it was perhaps less educated. These are all things that have been associated with the Brexit vote. And then we sort of put those in our variables, we perform our analysis. But arguably there's kind of an interplay between these things. And actually, as we start to understand, we need to go backwards and forwards between all of these. And I'm conscious on the projector, the arrows are not showing, but there's basically a two-way process between these elements. And so if we want to understand, we need to look and we need to see really what these relationships look like. So I borrowed a couple of visualizations that talk about this question of education and deprivation as being related to leave. So we can see in a sort of 2 dimensions, these are the correlated variables. Education was kind of the biggest driver. Strength of association with leave was the strongest. Deprivation in this paper by Calvert, Jump and Michel was quite strong. But then you start to visualize this picture, and that was saying that there was a positive association with deprivation. But actually, when you started to look at how many people, percentage of the population were educated and the leave vote, the education variable, the deprivation variable started to go the other way. Now, that was quite an interesting result, and that's taken from the UK in a Changing Europe, but the paper is referenced as well. But of course, that's just a story with 3 variables. So it's a little bit better than the 2 variable story, but it's still only 3 variables. What we really need is something that can allow us to think about this in multiple dimensions. So we'll come back to Brexit later, but this idea of visualization that I made in the argument is actually from Anscombe. Okay, this example is Anscombe's famous quartet, in which there are 4 different scatter plots there. Each one of them has a single x variable on the horizontal, a y variable on the vertical. And then what we see is an identical regression line with identical R-squareds and identical summary statistics for those variables. Now, the point was all of those, the quartet, actually convey different information. But if we just blindly ran the model, having assumed that our x was the only relevant variable, we run the risk of assuming that we've done really well and that we've got, the model that we desired. And so what we really want to do is start to think, well, how can the shape of data, what we were seeing essentially in the scatter plot, inform our discussion? So take this example. Now, this example is a series of scatter plots. These are 4 of many. And if we had to think about what was the odd one out here, so look around the room, and essentially, some of them look like they might genuinely be 2 variable data sets. Some of them look a little bit artificial, shall we say. But this image and what this shows us, in fact, is that actually summary statistics are not that useful. Essentially, the second order summary statistics are not particularly useful because all of those actually satisfy this question. So if we're introducing this to students, we build this and then they seem quite surprised, because if you ask somebody to think about 2 variables with a given mean, a given standard deviation, and a given correlation, the picture that emerges is very rarely one of those. And yet they are. That data set, they satisfy. Okay, so where Anscombe was telling us, with the univariate case for modeling, we needed to think about a single x. The Matejka and Fitzmaurice datasaurus just reminds us that summary statistics are not sufficient for telling our story. So what I'm arguing now is we've got 2 sort of historic results that point to the need to look at the shape of data. So we just add a few more different images from the datasaurus dataset, from the Matejka and Fitzmaurice, and there's a little R screenshot just to confirm for you that there is indeed the same summary statistics on there. Okay, so we're kind of aware now that we do need to think about shape.
Hi.
But when we think about shape, we probably...
I'm just listening to an AI talk.
Well, that's nice, yeah.
But it's fine because I've got my headphones on. So
anyway, so we would take, we do scatter plots and we would plot these things. And we start to talk about things like correlation and these in sort of basic concepts of statistics. And we do this with a view, again, to understanding our data. We want to know, is there a strong relationship, a weak relationship, etc. So way back in statistics, we view data. Anscombe said we should do it. The Matejka and Fitzmaurice, they sort of say we should do it as well. But as I mentioned, when we switch to a 3rd dimension, things become a little bit more difficult. Now, this is a 3-dimensional scatter plot of some normally distributed random variables, but it becomes quite difficult to talk about what's going on there. Yeah, we're not very good at seeing in 3 dimensions. One thing we could do is to split that and do the 3 pairwise plots. But if we do that, we miss the information on the other variable. Okay. Now, in this case, that was random normal distributed variables, so it's nothing much lost by going to the 2. But we can easily come up with artificial examples in which you would lose information. We can imagine 2 lines crossing each other that don't cross, but when we put them into 2 dimensions, they cross and you look like an X. And we can do that with 4 dimensions as well. It's artificial, but it reminds us of the need to see this thing. So, as I said, the arguments of this talk are that we need to overcome this inability to see in multi-dimensions if we are going to really understand what's going on in our data. So we move to, if you like, this geography notion that if we can map data, then we can understand what's going on in the space. So we can imagine that a scatter plot is a 2-dimensional map of our data. All of the coordinates are based on values in the data. And therefore, what we're going to do is produce a multiple dimensional version of the scatter plot and then seek to represent that in 2 dimensions so that we may see the result. So this is a very brief version of the algorithm. This is the topological data analysis ball mapper algorithm, initially introduced by Dlotko 2019. And as I said, because of the time, I'm not going to go through the full details, but in essence, we take a data set, and this is in 2 dimensions, so you can see it. We cover it in a series of balls. So in 2 dimensions, they are circles. The balls are centered on randomly selected points from the uncovered set of data. Once we have a ball, that ball covers some data points that are contained within it. And then we continue this iterative process of creating the cover. Edges, they're the lines, they join balls which have points in the intersection. We can use information on the number of points within a ball to size the points. And we can use functions of values of those points in order to create color. So we can imagine that the color on this plot is a value of an outcome of interest. Let's say the Brexit vote, and then we can represent the ball by the average Brexit vote within that ball. So this is the algorithm. Plenty of places where it's done in slower, but because we've created a cover that tells us everything about the connectivity, where those points are, takes the information of the other points and links that, we can produce an abstract representation. Now, in 2 dimensions, you wouldn't do this because this version, this abstract version where I've got rid of the axes, really has less interpretation than the 2-dimensional. But if we take this into multi-dimensions, then the ability to show those balls in 2 dimensions as circles, show that connectivity, and therefore understand what the what's in the data and how those outcomes map across the space actually starts to have value. Yeah. And what we're going to do in the examples that I'm going to quickly show you is to map some multivariate data sets. So that's the algorithm built through 2 dimensions. This is an example of a 5, but where it gets powerful is that where you start to see cases of interest where there's an outcome that's perhaps unexpected or a bit different, then we can zoom in and we can understand all of the properties because we know all of the information about the data points that were in that ball. So going back to the original plot. So here I made an artificial example where there's clearly a red ball of interest, and we can say, well, okay, here's a table, what is in that ball? And then we can see a sort of overlap to that sort of blue colored ball, and we can find out which points are common. And if we were, if this was a target, something we wanted to target with policy, we would be able to do that efficiently, not by just segmenting on 1 or 2 variables, but actually, zooming in on what exactly was going on. Okay, I say that's an artificial example, but it's surprising how often you obtain something like this when you start to, look at real world data. So, we've said again, we go back to Anscombe's quartet, and we can very quickly just see Anscombe's quartet using ball mapper because it's only a single variable. So the ball mapper plot is a chain, but we can understand that in the case of the noisy data for the regression line, color looks quite smooth, going from like a rainbow from red to blue. Where you've got a nonlinear, we can sort of see that in the top right panel, where you've got one observation, the outlier with the high value, you can see that on the bottom left, picking up the purple color. And then where you've got that leverage point case, the 4th one of Anscombe's quartet, of course, what happens, all of the data is concentrated at one value of X, therefore the big ball. But in fact, you can see that with the outlier, the leverage point is shown separately. So ball mapper actually helps us to see Anscombe's quartet, although we wouldn't necessarily need to for a single variable. So there's lots of things we can do. So in my work, we take like multiple observations of a variable over time, and that, if you like, is a trajectory charting the way that the things developed. So Here you can see just 2 time periods, and you can see these are the points that are in different balls of regional development, showing their GDP here in 1980s and 2000. And you can see different groups have gone together, and then we can know all about those regions. And with that paper, working with Don Webber of Sheffield, we just showed that resilience isn't sort of monotonic across this space, and most balls have a fairly sort of average recovery from the global financial crisis. And it's really a lot of variation given the trajectory. But the ball is helpful because it helps us see those trajectories. Okay, if we look at firm failure and the Altman Z-score model, so taking it from finance, here in this paper with expert systems with applications with Wan and Q and Paldlotko, we showed that in fact, firm failure is concentrated in a very small part of that Altman 5 ratio space. So again, the red firms didn't really fail. There's a very low proportion of failure there. Those blue and purple, that's where the failure is. So we've got this sort of thing works well with credit scoring, and we've discussed a lot of this with industry, because this is something that is powerful when you start to think, well, where is a firm and how can we understand risk? Let's just zoom that in. And here now is the Brexit result. So probably about wrapping up. I know we have the late start, but this is the Brexit result. So here you've got the leave vote per constituency. The axes that go into this are actually 27 different characteristics of the constituencies taken using census data. And what we see are those oranges, those yellows, those are the leave vote. They're the area where, on average, the constituency voted for leave. And you can see quite clearly, these are big balls. These are in a small part of the space. What we've got is a high concentration of constituencies with those characteristics that were voting for leave. When we look at the remain vote, the blue, well, that's quite spread out and doesn't connect well. And in essence, that shows us just how heterogeneous the vote for remain was. And for those who are interested, there's again a blog on the UK and a Changing Europe. We've got the paper forthcoming, where we show actually everything about these constituencies and why, in fact, you get this multi-arm perspective. But as you start to look at things like the election results, we can map those because we know the constituencies. These were the majorities for Labour in the 2015 election. And you can see that Labour's enjoying quite a large vote share, sorry there. But as we look at the Conservative vote, that was up towards the top. So you can see it's splitting on demographics about like we might expect. It's always reassuring when data does that. But then as we look at where the Conservatives made gains, you can see them making gains in that Brexit area, in those particular balls, quite concentrated. That's 2017 versus 2015, and that's 2019. So this is how the red wall fell. But interestingly, you also see Conservative gains over on the right in London. That was back in London, where other factors coming into play. So essentially, we have this thing, and we have a lot of sort of research going on, and I'll be very happy to talk more with people about this. But essentially, you look at the joint distribution, you map it, you understand what's happening there, then you can start to perform modeling on that distribution. And we have work that looks at modeling within balls. And then once you start to see patterns and outliers and things, we can appreciate balls. And in some of our other work, we actually look at how things like machine learning models are fitting across the space. So there's a lot there, a lot to talk about, and I hope that's given a nice flavor of the work that I'm doing and that I'm continuing to do now in Manchester.
So second speaker is Xian Yang, who did her PhD in Imperial, then spent some time in Microsoft in China, then went to, I guess it was a postdoc in Hong Kong, or assistant professor in Hong Kong, and is now in the business school here in Manchester, and is going to talk to us about towards personalized healthcare, AI-based approaches. And here's
thank you.
Thank you.
Yeah. So hello everyone, can you hear me? Okay, that's great. So thanks for inviting me to give this talk. So my name is Xian. I'm lecturing data science at Alliance Manchester Business School. So I newly joined University of Manchester last August, and my research interest lies in the area of machine learning, artificial intelligence, and data mining with a specific focus on healthcare applications. And today I would like to introduce some of my recent work in this topic, which is AI for healthcare. I'd like to start my talk by briefly introduce myself. So I received my PhD degree from Department of Computer Science at Imperial College London, and during my PhD study, I participated in a lot of precision medicine research projects. And after graduation, I worked as a research associate at Data Science Institute at Imperial, and later I joined Microsoft Research Asia, and at that time, working as a researcher in doing research in AI for IT systems health. So this slide actually summarizes the work I've done during Microsoft. So I have analyzed a lot of text data that generated from Microsoft cloud systems, and we constructed a lot of predict model using text data to predict incidents, outages, and also low capacity of the Microsoft Azure system. So although I will not give deep dive into those topics, I want to emphasize again. So all the models have developed for the IT systems health can be naturally extended for the human health as well. So we have published all our work in top tier computer science conference, such as FSE and WNW. And after I left Microsoft, then I pursued my academic position at Hong Kong Baptist University and later at the University of Manchester. So my current research area really lies in AI for human health. So I've done intensive work in constructing computational models in precision medicine, which is also called as personalized healthcare. So today, I want to briefly mention 4 typical tasks under the scope of precision medicine that I have implemented. These tasks are patient subtyping, also can be called as patient stratification, and phenotype notation, disease risk prediction, and drug recommendation. And I also want to briefly mention the work I've done during COVID-19, because at that time, I know a lot of researchers from different domains are very interested to understand the transmission dynamics of COVID-19. So did I. So I have been involved in a lot of research to estimate the transmission dynamics of COVID-19. So I've touched that a little bit as well at the end. So first, let me focus on introducing personalized healthcare and all the typical tasks I have participated in. Just a little bit background at first. So precision medicine, which is different traditional healthcare, which aims to provide the treatments for patients from same treatment for patients from same disease. Personal healthcare tries to design personalized healthcare pathway for different patients based on their molecular and clinical profiles. The typical inputs for the precision medicine research includes unstructured and structured data sets. So we have been working on structured data sets, including like diagnosis codes, precision medicine codes, precision codes, and lab test results, and also some omics data. For unstructured data, I've been intensely working on the clinical notes that generate by clinicians and nurses, and also a little bit medical images as well. A lot of AI models, basically deep learning models, are being developed these days to tackle different subtasks under the scope of precision medicine. So typical task is that using RN, Xian, transformer-based approaches to predict disease diagnosis results, predict mortality ratio, readmission, length of stay, and patient subtyping, and etc. So in the next slide, I want to introduce my first work, which I did during my PhD and the postdoctoral periods. So at that time, working on the patient subtyping, mainly using the multi-omics data. So one of the projects participating during my PhD is called the UBEPRED project, which is to identify subgroups of severe asthma. So this is a really big project. We have a lot of institutes from across the whole Europe involved in this project. So my role is working as a data science to construct computational models to identify the subgroups of severe asthmatics. So we collected multi-omics data, so includes the lipidomics, proteomics, transcriptomics, and also like breath omics, metabolomics. So we put all this data together and construct a lot of computational models based on different approaches, including machine learning to find the subtypes of severe asthma. So inspired this project, we have also initiated another project. So I also participated during my PhD and my postdoc period. So we have this project, which is called ITRIS project, to construct the knowledge management platform to facilitate precision medicine research. So this is the European's largest knowledge management platform at that time. It's founded by IMI. So I'm being intensively involved in constructing the analytical engine. So I've constructed a lot of data analysis pipelines that can be reviewed in many precision medicine research projects. So we have published our findings a lot of top-tier conferences and journals. A lot of computational models has been developed, including TDA that's introduced by Dr. Simon just now. So topological analysis has been used in our project as well, but I'm not an expert in that. So at that time, remember that we simply use existing software to perform the topological analysis and identify some subgroups of the patients. So the example shown here is using the lipidomics data as the input. Apart from using existing model, we also construct our own computational models. So like we use deep learning as well, like the figure showing here, use the framework of variational autoencoder to encode the patient's heterogeneous data from different omics formats and try to map those high dimensional data into low latent representation space. And by imposing the construction laws, we would like to learn the latent space that can best represent the patient characteristic and using the latent space to perform analysis. So the work we've done many years ago, at that time, the deep learning is not that popular. So we just use a very standard variational autoencoder to do that, to handle those multi-omics data. But we also published some paper in some conferences and journals. So recently, in recent years, I just moved from using multi-omics data to electronic health record data. Electronic health record, which EHR, contains data of different modalities. So I'm been intensely working on medical notes, which is unstructured text data. And also we use the structured data, including medical terms, which composed of disease codes, procedure codes, and medicine codes. Apart from that, we also have the numerical data, which can be collected, generated from lab test results or like ECG readings. So I have also done a little bit in the medical image, but I don't want to mention it today. So last year, I've been basically focusing on analyzing unstructured text data. So we have our first work is develop our own deep embedded clustering method to identify subgroups of patients while taking the unstructured text as the input. So in order to improve the performance of the deep embedded clustering, we train the model in an end-to-end manner and also adopt a contrastive learning approach. We also integrate the model with the embedded topic modeling approach to constrain the latent representation of cluster centers. So not only the performance will be improved, but also the results is interpretable. So we have published our work in one of the top NLP natural language processing conference last year. And based on that work, right now we are working with people from Nanyang Technology University in Singapore. So we use their data connected from the Chinese medicine clinics to identify subgroups of patients. So we construct our own multimodal contrast learning approach to identify patient subgroups. So this paper is still under major revision, so I will not introduce it in detail. Okay. So let me move to the next subtask I've done in my previous study. So when we're supposed to get imperial, I'll be also involved in constructing model for phenotype annotation. So phenotype annotation is trying to construct computation model to automatically identify standard medical terminologies or concepts from unstructured medical notes. So the input of phenotype annotator is just the unstructured descriptions written by the clinicians. So they would have the problem of like abbreviations, synonyms, and the typos. So our work is trying to identify standard medical terms from all those unstructured medical notes. So where you can see that expected outcome is like standard medical terms, anomaly of a cardiovascular disease, etc. So how to do that? A lot of natural language processing methods can be applied, including name entity recognition, information retrieval, and text classification. So we have also made our efforts under this topic. So we have constructed our transformer-based approach. We'll adopt the clinical birds that has been trained in the large corpus of biomedical data. So we apply this approach to encodes the unstructured medical notes. Our contribution lies in introducing data augmentation technique and also incorporating the knowledge base to boost the performance in detecting rare medical terms. So data augmentation approach we develop is try to reparaphrasing and generating some artificial EHRs this is together, the artificial EHRs together with the real world EHRs can be used as a training data set. By using the data augmentation approach, our training data set can be diversified, and our model adopt different training objectives, including the binary classification objectives to identify whether the input can be related to a standard medical concept or not. And also we have another object which uses the cross-entropy loss to identify whether the input can be from one of the most frequently used medical terms. So to increase the chance of detecting rare medical terms, we include the knowledge graph as well. So we use the knowledge graph embedding to generate the embeddings of standard medical terms and try to match it with the output from our real clinical test model. So the clinical bird-based model. So all this together has boosted the performance of phenotype annotation. So we have published our findings also in the top NLP conference in 2021, which is EMLP. Now let me talk about the third task, which I'm still actively doing right now, which is disease risk prediction. So I'm very keen to use multimodal data from EHR to predict the disease risk of patients. The multimodal data includes unstructured data, structured medical terms, and also the numerical data generated from lab tests. So our first work tries to construct a label-dependent attention model to predict patient disease. So this model is trying to make a balance between the prediction accuracy and the interpretability of the results. So the label dependent here means that we use the descriptions of the prediction task as the guidance to help the model to identify which inputs features can be associated with the prediction task. So we use the variables again to embed the unstructured unstructured medical notes, the medicine terms, and also the descriptions of prediction task. Altogether, we use the cross-attention mechanism to integrate those multimodal data and construct the predictive model based on neural network. The research, the output of this model will not only generate the risk of disease, but also generates the attention map indicating that which input features can be most likely associated with the risk. So right now, I'm just moving towards this direction using more data sets. And also, right now, the work I've just finished is based on the prompt learning to integrate multimodal from EHR. Because this work is just about to submit, so I will not introduce here. But I want to emphasize that prompt learning, maybe you have heard that already. It's used in ChatGPT right now to boost the performance of a lot of NLP tasks. We use as an instructor to guide the model to make the prediction or do the generation task. So we use prompt learning to generate the disease risk prediction results. Yeah. So we also published this work in one of well-known data mining conferences in 2021. The next task I want to introduce is drug recommendation. So drug recommendation is to suggest appropriate drugs or medicines to patients based on the patient's clinical profile. So we treat the drug recommendation task in the framework of network representation learning. So we constructed the EHR network where the nodes can be of different types. The nodes can be patients, disease, and medicine. And the link just used to indicate their co-occurrence. So after construct the EHR network, we develop our own target-aware network embedding method to learn the representation of nodes in the network and hence facilitate recommendation. In our model, we assume that a single patient node cannot be represented by a static representation. Instead, the representation of a patient node should depend on the target that we want to recommend. So we propose the target-aware approach where the patient here, this is just a single patient's embeddings, can have a lot of different embedding vectors. And those embedding vectors are learned in different drug recommendation tasks. And those embeddings just be dragged towards the direction of drug embeddings. So this is motivated by the fact that the representation for a patient's node, when used to recommend a drug that treating diabetes, should be different from the one used to recommend drug that control the blood pressure. So we develop our own target-aware network representation learning approach. And this paper has just been accepted by the SWSM this year and will appear very soon. And right now I'm still actively doing research in this direction. And we're just writing in preparation of this new paper, which is build our own heterogeneous network embedding approach for drug recommendation. So this is the typical task I've done in the area of computational models for precision medicine. So at last, I also want to talk a little bit about the work I've done during COVID-19, because I'm from Imperial College, and at that time, a very well-known professor is very keen on constructing the epidemiology model to predict the transmission rates of disease. So I also feel very interested in this topic. So because and the parameter of my particular interest at the time is RT value. So RT refers to the instantaneous effective rates of the virus. So maybe you have heard this RT value very often from some newspaper reports like in the BBC. You may heard that if RT value is larger than 1, then we need need to impose some external interventions to suppress the disease of COVID-19, spread of disease. So if it's lower than 1, we say, okay, right now the prevalence of disease have been well controlled. It's very important to understand and know the accurate value of RT value. And when we look at this, then we find the existing approach has suffered from 3 issues, which are lagging, averaging, and uncertainty. So lagging is basically resulted from delayed reports of the infection cases. And averaging is resulted from the introducing a lot of smoothing methods, like sliding window-based method to generate a piecewise curve of RT. So the instantaneous change of RT cannot be learned. Actually, this graph here is obtained just copied from a Nature paper published by Imperial. So it can only generate piecewise RT value, so which is not efficient for an accurate decision making. And the third uncertainty is that it resulted from the noisy observation. It's not clear here, but you can originally there are a lot of sharp changes there. Like in Sweden, we found that during weekends, the number of reported cases is much lower for the weekdays. This is because a lot of missing reports happen during weekends. So to deal with all these issues, we construct our own model. So we adopt the approach of Bayesian data assimilation. So we use the Bayesian updating approach with backward smoothing. Not only the RT value can be learned, but also its confidence intervals can be learned, and we were able to introduce auxiliary mechanism to indicate abrupt change of RT. So we have published our papers in some work in some journals. So that's what I want to say about my research interests. Just a short summary. So I'm being active doing research in the domain of computational models in precision medicine, and all the techniques I'm been using is related to natural language processing, graph neural network, multimodal learning, and a little bit about statistical modeling. So that's all about me. Thank you. Yeah.